So yesterday after doing this coin change problem, we were doing another problem of activity selection. So where, uh, what is the problem setting? You have n requests. So each request comes with a start time and finish time. And you have a single resource like a classroom where you have to schedule these requests. And of course, you may not be able to schedule all the requests. So the optimization problem that we had was, yes, I want to select a compatible subset of request that is your maximum size, right? So that is the problem that we defined. And we define what is compatible, right? Using this figure and the condition, you can see that. And of course, we just talked about brute force solution that is very inefficient. But yeah, that will give you a solution. So that's where we were. So today, let's start from there and think in terms of dynamic programming, right? So only for this greedy problem, I'll do in terms of dynamic and then go to greedy. But then after this, we will directly talk in terms of greedy. Okay, so this is just to help you transition from dynamic to greedy. Okay, so let's think in terms of dynamic programming, how you would solve it. So for that, let's again define that very formally. So you have n requests. And because you have to formulate in terms of dynamic programming, so it's better you make some order, right? So you say that, okay, they are sorted in some order. So either will work. So let's say, so we have n request. So each request I has a start time and a finish time. And of course, Si is less than Fi. And assume that they are sorted in terms of their finish time. Okay, I'm sharing my screen. Yeah, maybe you have to rejoin and then this might work. Sure. So assume that anybody else also having this problem cannot see my screen. So now assume that these activities are sorted in terms of the finish time. So we have the activity A1, A2 up to AN, and such that F1 is less than equal to F2. So they are sorted in terms of their finish time. Fine. Now, um, from there, what I need to do, I need to find out a compatible subset of request that is your maximum size. So in terms of DP, I'll think in terms of defining my subproblems. So defining subproblems. So now because they are sorted, I can talk in terms of some ij, right? And then I can extend to the entire set. So one way I can define my subproblems is this. So let's say Tij, set of all requests that, so because I'm sorting as a finish time, so the way I'm defining is slightly non-intuitive. Set of all requests that start after AI finishes and finish before AJ starts. Okay, so this is my subproblem, Tij. Set of all requests that start after AI finishes and finish before AJ starts. For this subproblem Tij, let's say define what is an optimal solution. So Sij is an optimal solution, let's say. And this is just a subset. So Sij is just a subset. So compatible subset of maximum size. Okay, but finally, what do I need to know? What do I need to know? Do I need to know the subset or something else? What is my final solution here?
The number of elements in the subset?
Yeah, I want to maximize the size of this subset, right? So corresponding to this, let's say my final solution is Cij, and that is nothing but Sij. That is the size of this subset. And of course, I want to maximize this Cij. Yes, right. Now, so in dynamic programming, you start by thinking in terms of what would be your subproblem, right? Most important thing. Now, in terms of your subproblem, you should be able to express your final solution, right? So what is your final solution here?
C1n.
C1n. Anybody disagrees with this?
Sir, it finishes before AN starts and starts after A1 finishes. So
Right.
how can A1
So
and
you see,
A1?
the way we have defined Tij, it excludes both AI and AJ, right? So set of all requests that start after AI finishes, so AI is not included, and finish before AJ starts. So AJ is not included. So that means, oh, C1n if I take, that will exclude A1 and AN. So A1 and AN are excluded. So how can I define my final solution then?
It will define in terms of an index and the final time of the last task.
Sorry?
Means the finish time of the last task and one index will define that way. It will be better.
So what I will do here, so I say, okay, fine, I have activities A1 to AN. Now, I can find out what is the minimum start time of any of this. Let's say what is the minimum start time for any of this. Okay. And what is the maximum finish time of all of this?
Fn.
Fn. Fn is the maximum finish time. So no activity finishes after Fn. And minimum SI is the minimum time for the start for any of the activity. So what I will do, I'll define two dummy requests. So let's say A0 such that its finish time is less than equal to minimum of SI, and AN plus 1 such that start time is greater than Fn. Yeah, equal to also will not matter. Right. So I define these dummy requests. Okay, they are not there in my original set, but I just define it for the sake of defining my final solution. So these activity, so A0 finishes before any of this starts, and AN plus 1 starts after everything finishes.
Sir,
Yes.
F0, can we say F0 less than equal to F1? Since
Can we
F1
say?
is
Can we say?
F0 is less than equal to F1.
No. What we are saying, so you see, you don't want A0, AN plus 1 to interfere at all, right? By this, you are ensuring that it finishes before anything starts. So A0 will not even come into picture of your solution. Okay, so let me, so what you are saying, so I think is not clear. You are saying, why don't I define like this? F0 is less than equal to F1,
Yes, sir.
right? Okay. Let's take your point. Now, what will be my final solution? What is my final solution?
C0 n plus 1.
U0 and
Zero
plus
and
1.
plus one. Okay. Now, go back to the definition. What is that? All activities that start after A0 finish. So activities that start after A0 finishes. Now what you have ensured is that A0 finishes before F1, but A1 might start earlier. So then A1 will be excluded from here, isn't it?
Yes, sir.
Right? So that's why I cannot define it in that way. So that's why I'm defining F0 is less than equal to minimum of Si. So that, okay, it will start before anything, it will finish it before everything starts. So this is not good. So I'll do somewhere here, F0, and I know all other SIs are larger than F0. So that way this final solution will valid, this will not interfere. And same happens with n plus 1. We start after A0 finishes and finish before an plus 1 starts. Sn plus 1 is always greater than equal to Fn, so everything is finishing before an plus 1 starts. So that way I have defined two dummy tasks or two dummy requests, A0 an plus 1, that are not interfering at all with my set of activities, one to one. Is that okay? Now I can define my final solution to be C0 n plus 1. Any doubt here? Okay. Now, how will you, what will be your re- recursive formulation? What will be your optimal substructure? So you suppose you want to write, okay, fine, I defined my final solution C0 n plus 1, but you have to finally say what is the recursive formulation, what is Cij? How will you write Cij using your dynamic programming? So remember, activities that start after AI finishes and before AI starts. All activities are there in this set Pij, and you have to select Sij is the subset of maximum size, compatible, and Cij is nothing but the size of the subset. So how will you write your Cij? What is the recursive formulation of Cij in terms of subproblems? How do you write that in DB? In between there will be many activities, let's say, right? So how will you write your DP formulation? So you see what all you can do, right? What all you can do. So let's say, okay, let's take in K between I and J, right? And I choose AK. Suppose I choose AK in my final solution. So then, so there is some K, AK that I am choosing. Suppose I choose AK. So what? How can I write Cij? I chose one activity plus
Cik plus Ckj.
right. So now I will see what is the optimal solution for activities that start from here and finish before AK starts, plus start after AK finishes and finish before AJ start. And AK has been chosen. So 1 plus C of IK plus C of KJ. Okay, if you choose a CK. Now, in terms of dynamic programming, how do you formulate this? This is by choosing a particular CK. Now, what is your final solution? What is your
Maximum when we vary k from I plus 1 to j minus 1 and we'll take max of them.
So, maximum of this where k varies from all possible k's between I and j, right? And this will be 0 if I is equal to j. This will be 0. Is that a correct DB formulation? Anybody has a problem with this?
Sir, if I greater than j, still it will be 0.
Okay.
AK can start before
Right. I
I
mean, you
ends.
can define how you will fill your table. I mean, so okay, you can say I get equal to.
Sir, how do we guarantee that AK starts after I ends?
How do we guarantee that AK starts after A ends? See, that is how we are defining, right? That is how we are defining.
Okay, so AK is a part of TIJ.
So TIJ has all the activities that start after AI finishes and finish before AJ starts. So that's it.
Okay, sir. Okay, sir.
Okay, so what you're saying, I think, is that, okay, I should also mention that AK is a part of TIJ. Sure. Instead of that, I can just mention this.
Sir, if j is equal to I plus 1, then it also should be 0.
Okay, so you are saying if j is equal to I plus 1, then also should be 0. Maybe, yeah, this will be.
So because we are not taking k can be equal to I also.
Right, k cannot be equal to I, k cannot be equal to j. K has to be greater than I or less than j. Sure, that is also fine. That is also fine. Okay. So,
Sir,
yes,
sir, is it guaranteed that for all k from I to j that AK will belong to Tij?
no, no.
So how can we check that?
That's easy to check. I'll explain that in the code. That's very easy to check. You have to just see the start time of k. If it is, yeah, based on that, you can check this. In the worst case, you will have everything, right? But you can always exclude something. You can also always exclude something by seeing its start time. So, right. So I think what you want me to do, instead of this, I should say this. Okay, I agree with you. Let me write this. AK belongs to Tij. And what it means is that the start time of k should be greater than f of I, and finish time of k is less than SNG. It starts after AI finishes and finishes before AJ starts. So this is, you can check in constant time, right? And then if it is there, you put that inside your DP formulation. Okay, is that fine? Okay, now is there any issue? I think with that it should be okay. Yeah. So, and you can do your DP. Yeah, we are not actually doing finally DP, but you can do your DP. This will, how much time it will take doing this DP? What would be the complexity?
Order n cube.
Order n?
Cube.
Order n. Order n cube.
Sir, but
Because
this
you have
DP
to
can
fill-
be improved, sir, right?
Huh?
Sir, this DP can be improved, sir.
Okay, how?
Sir, we can define that AK is not just any one of the elements in TJ, but the last element in TJ. So we can eliminate CK, comma J, and it will just become maximum of 1 plus CI, comma K. And they can, and then we can fix I equals 0 for all.
Now you see, for that you are doing something else. For you, for that you are actually using something else. Right? If you just define in terms of DP, this is how you will define it. Okay. Now what
Okay,
you are
sir.
saying is something different. So if you just think in terms of DP, this is what you will come up with, and you will say, okay, this will be order n cube solution. Right?
So
And now,
So why this will be n cube? Shouldn't it be n square? Since if we choose any end of, if we choose the k which is near to AJ, then we will
see, for
have.
that you have to use a greedy property. So you see, this is the way you will define your DP. But what you are saying is a greedy. You are thinking in terms of greedy now. Yes, we will do better than that, but for that we will use a greedy property, right? So in this formulation, it will take order n cube, right? And this is how generally we will think in terms of DP. You can pick up any particular activity and define the complete solution, and for that you have to fill all these columns, order n square columns. Each one will take order n time. That's how you get order n cube. Now, what you are thinking, oh, I can do better than that, but yeah, that's where we are coming to greedy. That's why you will do better than this. Right? Okay, so I think you can't stop thinking in terms of greedy, so let me directly ask you, greedy. Okay. I thought you will only think in terms of DP, but you are thinking in terms of greedy. Okay, good. So now let's say, okay, so you are saying let's use a greedy property instead. Okay. So I have a set of requests. So A0, A1 up to an plus 1, 0 and n plus 1 are dummy. I do not worry too much about these. Just help me to define my subproblems. Now what you're saying, okay, I have now, suppose I have this sequence of activities. They are sorted as per their finish time. F1 to Fn are sorted. Now, instead of doing this dynamic programming based formulation and choosing the max, can I identify a greedy property that is guaranteed to be in an optimal solution? In an optimal solution. Property, or I mean a choice, a greedy choice that is guaranteed to be in an optimal solution. Okay. So now let's think in terms of greedy. Yeah. Now tell me, what is a greedy choice that I can take? So choose this activity with this property. So let's define some greedy choices. Greedy choice 1. Yeah. Now, tell me your greedy choice.
Sir, we choose a activity whose start time is just after the allowed start time, and
Choose an
like that.
activity. No, yeah. Just give me one greedy property. Choose an activity.
So choose activity A1.
A1. Choose activity A1. Right. Okay. So that means what you're saying, activity with the earliest finish time. That is your greedy choice 1. Okay, fine. Now somebody give me another greedy choice. Greedy choice 2. Unless everyone thinks, oh, this is the only possible greedy choice I can make. Anybody with another greedy choice? You are allowed to think.
Sir, can't we choose an activity that has
Start after
earliest
A1
start time?
and give the least F1. Least
Okay,
F1.
so let me write first. Choose activity with the earliest start time. Yeah, this is your greedy choice. I'm saying just give me your greedy choices. We will see which one is correct, which one is wrong, but at least give me some choices.
Choose an activity if its start time is greater than the finish time of the last chosen activity.
Oh no, that is coming inside 1 or 2. So forget about last activity that you have chosen. So you have a set of activities. You tell me one choice. So are you saying the one with the earliest finish time or one with the earliest start time? Which one you want? I think both of these are covered. So I don't think you have a different choice than these two. Anyone else? Any other choice?
Sir, we can choose task with the shortest duration
Why
first.
not? Right. I choose a task with the shortest duration. That means this will leave the resource available for longest time, right? So choose an activity with the shortest duration. Oh, 10 minutes activity. Yes, please. You can please, yeah, take it. 10 minutes. You will are leaving the resource for long time. I don't want a 1.5 hour lecture to take up the uh, room. So that means Fi minus Si is smallest. Makes sense. So leave resource available for maximum possible time. Anything else? We have 3 choices. Another choice. One more, and then we'll stop. Why don't I choose an activity that is having the least number of incompatibilities? All activities have some incompatibilities, right? This is incompatible with 1 activity or 0 activity with 2 activity. So I take an activity that has the minimum number of incompatibilities, so that if I take that, that removes very few other activities, right? So choose an activity with minimum number of incompatibilities. So that means we'll only remove, so that means if I select it, I have to only remove the activities that are incompatible and that are very few. We'll only remove minimum number of activities. So most of the activities are still in the hunt, right? Anyone can think of any other choice. So we have 4 choices, right? I don't know how many are correct, but we are going to find out. Okay, let's go bottom up, or you want top down? Yeah, bottom up or top down?
Top down, sir.
Top down. Okay. Let's take greedy choice 1. Choose activity A1 with the earliest finish time. You see, for each of the greedy choices, remember what I need to do? Let me write down the rule. The rule of the game is that for each greedy choice, either it is correct or incorrect, right? So if it is correct, give a proof. And if it is incorrect, what do you need to do?
Sir, counter example.
Give a counter example. So now, people who found out greedy choice 2 and 3, 4 is me. Can you find a counter example for 1? Counter example means you will give me one set of activities and where you use greedy choice 1 and it will not give you an optimal solution. Okay, I think we remembered the choices. So 1 is finish time, earliest finish time. Okay. Anybody can find a counter example for this, earliest finish time. So I have activities sorted as per the finish times. Right? So that means this is A1, this would be A2. Even if it starts before A1, it finishes after A2, A1. So, so what about this? I have an activity that finishes early, very early, it finishes very early, but there's another activity that goes on for much longer duration. And then there is another activity. Right? Now, what will be my solution? Won't I prefer this and this?
So we can take the shortest one and the last one.
We can take the shortest one also, no, sir. Like
Shortest
it's not
means
wrong.
the earliest finished. Earliest finished. We are talking about earliest finished. So by this you mean the earliest finished, right? Yeah. So what you are saying, I'm both right and wrong. So yes, I can take this, but I can also take this as my solution, right? This is also compatible subset. So even this is fine. So that means this is part of my optimal solution, part of one optimal solution. Even if I have another optimal solution possible, this is part of another optimal solution. So this is not a counter example. Anybody can think of a counter example?
Sir?
Yes.
Sir, here why aren't we are not thinking in terms of like I to j, y1, or it's like I plus 1?
Yeah, see, you can think in terms of I and j. That will not matter much. That will not matter much. That I will explain. So right now you think only in terms of all the activities. You have to select one activity. Okay, you can do the same thing thinking in terms of I and j. It will not change. You think all your activities from A1 to AN, all the possible activities in Tij. Okay, so this will extend to Tij also. Very simple. Here it is helping me to use simple notations A1 to AN, and I am using that. You can extend the same argument for Ti. So that's not. Anybody can think of a counter example? No. Okay. So we'll have to prove it then. If we want to show that this is correct, we have to prove. Unless
Yes,
somebody
sir.
comes with counter
So we
example.
can prove it.
Prove it. Okay. We have to prove it. We will prove it. Okay. I'll come back to the proof. We'll prove it. Good. Okay. So now let's take second one. Yeah. We'll come back to this. Second one. Earliest start time. So, is it correct or can you find a counter example?
Sir, we can take an activity which has earliest start time but ends at the last.
Wow. So yeah, someone who doesn't leave the room, or give me a room and I will not leave it. So Yeah, I'll start in the morning, early morning. I'll not leave the room until, yeah, your day is over. So this is your activity, one activity. Not, of course, not even, but then there may be other activities that we start later, finish. They are all nice guys. They are finishing in time, right? Now you don't want to be, be fooled by a person who's saying, "Oh, I'm starting early," but may take the whole day. So if you choose this by your greedy property, you see you're making a mistake, right? So you should choose this. So yes, very good counter example. So 2 is out of the picture. Okay, that was quick. What was third? The activity that takes the shortest time. So I am here only for 5 minutes. Give me the room for 5 minutes only. Right? So third, shortest time. What do you think?
Sir, it may be the case that the activity is highly incompatible.
Oh, I'll come back to that in 4, but yeah, give me a counter example.
Sir, we have two activities which are like first 10 and the second starts, but the at that time we are having another
Okay.
short
So
activity.
we are having 2 activities, just one after another. Literally no gap.
And we have a short activity
And
during the second activity.
then somehow say, oh, I wanted 10 minutes window, 5 minutes into him and 5 minutes into him.
Yes, sir.
That's all.
Yes,
Right?
sir.
And this is your setup. And then you say, oh, you want it only for 10 minutes, so take it. And then you are gone. You are selecting a non-optimal solution, right? Because the optimal solution is this. So good counter example. So this is also not a good choice. Now let's see fourth. The one that I gave. Activity with minimum number of compatibilities. Incompatibilities, I'm sorry. Choose an activity with minimum number of incompatibilities. Let's see in our solutions. Is anywhere I am already finding a counterexample. Okay, do I find a counterexample here in this? No. This is the activity with minimum number of incompatibilities. I can choose that. Then also I will get an optimal solution. Fine. Here, choose an activity with minimum number of incompatibility. This has 4 incompatibility. I will not choose this. And these have 1 each. I can change and this will give me an optimal solution. Let's go here. How many incompatibilities this one has? 2. This has 1, this has 1. So I'll again choose an optimal solution by this. So is that a correct greedy choice? Is that a correct greedy choice?
Yes, sir.
Oh, you are with me? Oh, we have found a second greedy choice that is correct. Anybody else has a different opinion? That's why greedy algorithms are so nice. So, so it turns out this is not correct. This is not correct. Even if I showed you 3 examples where it gives you 3 examples that I did not think earlier, on all 3 examples, this gives me an optimal solution, does not mean this is optimal. Okay. So just because your algorithm works for few examples doesn't mean that this is an optimal algorithm. So now let's create a counterexample. Okay. I want an activity with which is not optimal, which should not be in the optimal solution, right? Okay. So let's first create an optimal solution. Okay, so let's say this is my optimal solution. I have to select these 4 activities, and I want to make sure that my greedy choice picks up this. That means it will be non-optimal. Once I select it, I'll get a non-optimal solution. Okay. So what extra activities I need to add to ensure this? So now I see, okay, this is not making sense because this activity has 2 incompatibility and this has none. So my greedy choice will actually choose this. So I have to do something so that everyone has more incompatibilities. So let's do something. So let's add incompatibilities to other things. So
So we can make an activity across all of them and then add at the end and beginning of it.
okay, now what? Now what? Now this has 2. This has 2 incompatibility. Anybody with a fewer incompatibility still? Fewer than this. So you take any arbitrary thing. This one has 3. This one has 3. This one has 3. This one has 3. I will not choose any of this. Right? And immediately that means I'll get a non-optimal solution. And these have even more. These have 4, 4. So I'll choose this. As soon as I choose this, I'm done. That means I am going for a non-optimal solution with my greedy choice. Okay. So okay, I found a counterexample. So this is also
Sir, I did get this.
what you did not get.
So like we introduced these 3 black columns, black activities, and then how we are selecting these 3.
No. You see, think of this as your set of activities.
Yes, sir.
Okay. Now you have to find an optimal solution. What is the optimal solution here?
Lowest compatibility we will choose directly.
No.
So we
That
have
is my
chosen
greedy,
this
that is
middle
my
one.
greedy choice. That is my greedy choice. Please make a distinction between optimal solution and the greedy solution. Okay. Until we have proven that greedy choice is optimal. So now what is your optimal solution?
That 4 continuous.
Yes, good. So this is my optimal solution. Right? Now, what is my greedy choice? Greedy choice is I will choose the activity with the minimum number of incompatibility. Now, which one is that? I'll choose this.
Yes, sir.
That has only 2 incompatibility. Everyone else has more.
Yes.
Right? And as soon as I choose this, that means I can't choose an optimal solution. I have to choose this, this, and this, or something like that. This, and this. So I have to choose maybe this, and this.
Maximum 3, sir, with greedy.
Yes, sir. Yes,
I can at most choose 3. Yeah. But my optimal solution has 4. That means my greedy choice is giving me a non-optimal solution.
Okay.
And that's why it is a counterexample. Okay. So I want you to understand this distinction very, very clearly. You can define arbitrary numbers of greedy choices, right? But maybe more than one are correct. But for each of the choice, you have to either find a counterexample or prove it. Okay. Now, can anyone say is there any other choice that will also be correct? I'll not prove that, but there's actually one more choice that is correct.
So take the activity with the latest starting time.
Yes, very good. So pick the activity just the other way. Pick the activity that has the largest, the starts at the end. Okay. So I'll just write 1 prime. Largest, latest, whatever you want to call it, largest start time. Okay, but I'll not prove it. Prove is very similar, but that will also give you an optimal solution. But now let's go back to what we promised, that the activity 1, nobody could find a counterexample, does not mean it is optimal, right? For 4 also, you were not able to find a counterexample easily, but somebody else could. So that's why let's prove it, that 1 is actually optimal. Let's finish. Okay, my greedy choice, earliest finish time. Okay, Now I will come back. Somebody was asking about using Tij and all. Now let me come back to this Tij. Okay, now I will write it formally. So let's define. Let Tij. We already defined set of tasks. Start after AI finishes and finish before AJ starts. Okay. Now let's say let AM be an activity with the earliest finish time. Okay, and that will actually be no, I can't say. I can't say it will be I plus 1, right? Because they should start after AI finishes. So it may happen that I plus 1 was starting earlier. So let's say AM will be an activity with the earliest finish time. Okay. Now what I'm saying, then AM is included in some optimal solution of Tij. Okay. Suppose I can prove this. Yeah.
Sir, M lies between I and J, or it is completely arbitrary? Or it is 1, means...
No. See, M is not 1. See, I'm going back to my this DP formulation. Finally, I will show this is also not very important, but in terms of my DP formulation, I'm just showing. So the Tij was defined, right? Now AM is any activity that is in the set Tij. Yes, so that's how you can see. So of course, this will lie between I and J for sure, but this may not be just I plus 1. This may not be I plus 1.
Means here we are not assuming sorted input, right?
No,
Means
they are sorted, right? But the way I have defined it, so in Tij, start after AI finishes, right? So AI has finished. So
okay,
AI plus
understood.
1, AI plus 1 may start before it.
Before it, yes. Okay.
So that's why it may not be there. So that is why I'm saying that. That's how I'm in the definition. I'm in terms of Tij. This is not. This need not be AI plus 1. So AM is an activity with the earliest finish time, and then I'm saying AM is included in some optimal solution of Tij. If I prove that, that means yes, I have a greedy choice for my dynamic programming, where I was trying to find out all possible activities and taking out one as the max of that, right? So instead of that, I can just make a greedy choice instead of doing the max, right? So, so how will you prove it? Proof. How will you prove it? How do we prove for greedy optimality? We start with an optimal solution and show that, okay, if it is different from greedy, you can keep on modifying it to make it similar to greedy. So proof is let Sij be an optimal solution. Okay, so that means it is the maximum subset that are compatible and that are within Tij. Now I am proving only for this, that AM is included or not. Okay, this is the only thing I am proving right now. So then there are two cases. So case 1, or I can even say, to make it easier, let AM be the activity in Sij with the earliest finish time. which here would also mean this has the earliest start time because this is a compatible subset, right? So AN will be the activity, and don't confuse N with that N, so I'll just use another subset. Let A.
Sir, it need not have earliest start time.
Hmm?
It need not have earliest start time.
No, AO be the activity in Sij with the earliest finish time. So in Sij there are some activities and they are all compatible. If AO is the activity with the earliest finish time, it will also have the earliest start time, right? Why not? They are all compatible within Sij.
Yes, sir.
Right? In Sij there is an A0 that finishes the first. So nothing can start before that. So everyone else will start after that. Now there are two possibilities. Case 1, A0 is same as AM. Case 2, A0 is not same as AM. Nothing else can happen, right? Exhaustive possibilities. If the first case happens, A0 is AM.
Sir?
Yes.
Sir, you
A0.
have said that no activity can start before F0.
Yeah, this is my problem. I used the wrong notation. I was calling it AO, then I started calling it A0. I should use something else. Let me use AOPT. AOPT. Okay, it's not your problem, it's my problem. Okay. Is that okay now?
So, sir, you have said that no activity should start before F opt.
No, I said it for only A0. Yes, those were dummy activities. A0 and N plus 1 were dummy activities. Now that's why I'm using a different notation. I'm calling it AOPT. AOPT would be the activity in Sij with the earliest finish time. Okay, so there are two possibilities. Either this is same as AM or this is not same as AM. If it is same as AM, then what? My proof is done. Okay, done with the proof in this case. Because I was saying AM is included in some optimal solution of TIG. Yes, if AOPT is same as AM, yes, done. The problem is if AOPT is not same as AM, that is the generic case. In that case, how do I, what do I do? What do I do now?
We can replace AOPT by AM.
So now suppose AOPT is not same as AM. Let's further think what can happen. So this was my AM that had the earliest finish time among all the set of tasks in TIG. If AOPT is not same as AM, what can happen? Let's think in terms of finish time. Can it happen that FOPT is less than FM? Or
No, sir.
FOPT is larger than FM? Which one is possible?
Larger.
Why is this not possible? Because by definition, AM had the smallest, earliest finish time, right? So this is not possible, but this is possible. So then what might happen for AOPT, this FOPT is larger than FF, okay? But yeah, so that is the case. And anyway, all other activities are compatible, whatever I'm choosing. So this is my Sij. Okay, this is my Sij. Now, what I'm saying, fine. So what I will do, let's start from Sij. So let's start from Sij and replace AOPT by AM. So remove AOPT and include AM. So you define a new set. S prime ij is Sij minus AOPT union AM. Okay? Okay. Now, my question. Is that also optimal? So question, Is S prime ij also an optimal solution?
Yes, sir.
Suppose Sij was optimal, right? So then I removed one activity and added one activity. So Sij, S prime ij has the same size as Sij. So yes, answer is yes.
Sir, will this be valid for any ij? Since here Sij for the A start time will be after the AI.
Okay, I'll come back to that. I have to ask another question, then I'll come back to your question. Second question is, for it to be an optimal solution, or for it to be a valid solution, it should be compatible. Okay, is S prime ij also a compatible subset? Sij was compatible. Is S prime ij also guaranteed to be compatible?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
Because all activities were after the finish time of finish time. And here I'm choosing an activity that finishes even earlier. So this will remain compatible, right? So answer is yes. Anybody has a doubt here, you can just ask. I'm choosing an activity, the first activity. I'm replacing it by another activity that even finishes earlier, right? And everyone else starts after F opt. So anyway, there will be even a much larger gap between activities. Right? So this is going to be remain compatible. So this is also compatible. So that means S prime ij is an optimal solution also.
Sir, here A opt is the first element of Sij. Means Sij is the
No.
compatible.
Oh yes, yes. E opt
And
is the first element of Sij. Yeah, the one that finishes early, and yeah, that also means that it starts the earliest. Yeah.
yes, sir.
Okay. Okay. Now is my proof done? So that means I can start from Sij and construct another solution that is also optimal and contains Am. So S prime Aj is optimal and contains Am. So that means I can go back to this, my statement, Am is included in some optimal solution of Tij, and this is proven. This is proven. So that means my greedy choice is optimal. This will give me an optimal solution always. Okay. And that is all I need to do for my proof.
Sir, is it not required to put a condition that AM starts after AI finishes?
No, because I have already defined Am to be that, right? Am should be following that. Am is the part of Tij. Am belongs to Sij, and what it implies is that Am belongs to Tij. And by definition, all the activities in Tij, they start after AI finishes and finish before Aj starts.
No, sir. While comparing with S prime ij, Sij and S prime ij, and we took Sij with starting element as A opt, right?
Yes.
Before that itself, we choose AM to be part of Tij. Is it?
Yes. No, Am was an activity in Tij that has the earliest finish time. That was how I defined Am.
Okay, then it is.
Okay.
Thank you.
It was not part of Sij. You see the definition? Am be an activity with the earliest finish time, and that was for Tij. We didn't have Sij here. Let me explicitly write it in Tij. Okay. So my proof is done. So I have a greedy choice that can help me solve the problem. What is the complexity now? What is the complexity?
Order n after sorting.
Okay. So yeah. So now good thing what you said is that, okay, see, I did all this starting from dynamic programming and coming back to this solution to show that, okay, you can think in terms of dynamic programming and you can have a greedy choice. So instead of this max, where we had this max, right? I can simply choose the activity with the earliest finish time. Yes, I can choose the activity with the earliest finish time. And that way I can ignore max, and this will give me order n square. But then I can go one step further and say, oh, wait a minute, I don't even need to define all these subproblems now. I have a set of activities 1 to n. I choose the one that has the earliest finish time. So I can do it in order n if they are sorted. Okay, so that's where I further for greedy examples I'll not start with TP. I'll maybe directly start with the greedy part. So what will be the greedy solution? Greedy solution. Yes, let me just write a quick pseudocode. So activity selection. What is the input? You need the start and the finish time arrays, and we sort it as per finish time. Okay, and let's say you are storing your answer in A. So you select which activity? The first one. I mean, whatever. I mean, select activity 1. Always. And you store something like last selected was 1. Okay, so that means 1 is selected now. Now you have a loop from for n is equal to 2 to n. Now for each activity, you have to make one check. What is the check? If
Starting is greater than
start time is greater than
Finish time of last selected.
Last selected. Right? Then A is equal to A union M, and last selected is equal to M. Is that all? And that is all I need. Yeah, that is all I need. If they are sorted, and this, if you can see what is the complexity, order n. If activities are sorted as per finish time.
So we are given the initial array with sorted finish time, or we shall sort it.
So that's what I'm saying. If you are given that as per sorted, as per finish time, it will take order n. But suppose you are not given, then but yeah, order n log n if original array was unsorted.
Sir, then in that case, we also need to establish the relation between start and finish.
What relation you have to establish?
Sir, I mean, we don't have only one array to solve.
You will have an array means you will have all the activities. You will have their start and finish time. You will have 2 arrays or whatever is structure, an array of structure. But you can just sort them as per their finish time in on order and log in time. And then you need these 2 arrays or whatever you want to call it, a structure with these 2 things, but it is sorted as per their finish time. It does not matter. And this whole loop takes only order n time. So overall order n, if sorted, order n log n if you have to sort. And that is much faster than the DP that we started. Okay. So yeah, so that's where we completed one problem.
Sir?
Yes.
Sir, if we wanted to implement this greedy algorithm with that same DP formulation IJ, then it wouldn't have been so like O of n, right?
Yeah, that's what I was telling. It would take you order n square. Yes.
So I think it would still be O of n cube only, because still I have to search.
Not order n. It will surely not be order n cube. Will it be order n cube? Maybe. Why? You are saying because for each k you will have to check which one is having the.
So yes, because immediately I plus 1 always not be the choice.
Okay, yeah, I mean sure. With some assumptions it will be order n square because, but yeah, in the worst case, I don't know, maybe order n cube. Fine. But anyway, you will not solve this with this. Sure. So you will solve with the simple one loop. Yeah, maybe you are.
Sir, S and F both are sorted as per finish time, right?
No. Yeah, yeah.
Okay.
I mean, they are just telling you the index of activities. They are as per their. No, they are giving you the. Sorry. They are corresponding to the activities that are sorted as per the finish time. So the first element of both the arrays will tell you the start time of the activity that finishes the first and the finish time of the activity that finishes the first, and so on.
Okay, sir.
Okay, any other question here? Because I think now it's time we should move to the tutorial. So I guess Kaushik is here.
Yes, sir.
Okay. So Kaushik, do you have, oh, I'll make you a presenter.
No, sir. I think I can't share right now.
Yeah, I'll give you the right. You can present now. I'll stop presenting.
Okay.
You can continue. Okay.
So you guys can see my screen, right? Hello.
I can see this.
Yeah.
Yes, sir.
Okay. 1 minute. Okay. I think you have till now been, sir has been teaching you greedy till now. So on that aspect, we'll be seeing in the tutorial we'll be seeing about a greedy topic, and we'll be primarily focusing on the last year lab problem and like the different ways to approach it, like the tips and tricks. And other than that, there are two HackerRank problems which I listed with hints, not in detail, but I'll explain the basic aspect of the solutions as well to you. I might go a bit fast, but please stop because I haven't done this in a long time. So please stop me if you have any doubts or issues. So first, let's look at the problem. So you're a shopkeeper, and as a shopkeeper, you have received a lot of requests, and they have placed certain orders to you, and you're about to deliver the orders in a particular day. N people are coming to get their orders back. But the catch is that they cannot come at any point of the day. They are only available at certain point of the day. Here, in this hypothetical situation, the day consists of m minutes, and m is a given constraint of 10 power 5. So the people can come between any. There will be a fixed range that they can come, which is denoted by LIRI. So this would be the range which they can come in, and only at this point of time, at any particular instant of this LIRI, they can come and get their order. And you as a shopkeeper has to decide at which point of the time they have to come, but at what conditions. So as I said, each customer comes and gets their order at minute xi, which obviously is in the range of their the time frame which they can come in. And for the case of the problem, you can assume xi is an integer. To be honest, this can be solved even if xi is not an integer, but for the sake of simplicity, we can assume it's an integer. And as a shopkeeper who is following all strict COVID protocols, you want to ensure that if the customer comes and gets their orders, the minimum time difference between any two customers, like if there are 4 customers, the time difference between first and second customer, second and third customer, third and fourth customer, it's minimum possible. Here, to consecutive customers, in the sense like the time which they come, like the first customer comes and gets, second customer comes and gets, and the minimum difference between them is maximum possible. I'll give some examples to elaborate this, but try to wrap your head around this for now. So what you have to do is, you have to design an algorithm to efficiently determine which time each customer has to come and get their order. Like obviously, the time has to be within the time frame where they are available, and you have to see what is the minimum time difference between any two customers. As I said, the minimum time difference should be the maximum possible, as mentioned here, is as large as possible. So this is basically the problem. So if you want the problem in more formal terms, you are given n ranges of the form LIRA, like your n ranges. You can treat them as segments in a 2D plane. Just imagine this as sorry, in a 1D plane, LIRA. And the LA and RA are considered from 0 to M. So you have to design an algorithm for each of the ranges. You have to output a particular integer which is in the range. In the range given to you for each of the ranges, and you have to output it such that the minimum possible difference between any two integers you have outputted is maximum possible. So this is basically the problem in 3 lines. So if you want, for example, if you look at this, there are these 2 line segments denote 2 customers. So, and this 412 is the range, the time frame available for the first customer, and 1020 is the time frame available for the second customer. So if you want to maximize the minimum difference possible between the customers, which is like this 2 customers, which is the minimum difference will be the difference between the actual customers, and you want to maximize that possible. So it's quite intuitive that you will have to place the first customer as early as possible and the second customer as late as possible, and you'll find that the answer is 16. If you since these 2 customers, it ended up pretty easily. But if you look at if you take example of 3 customers, suppose there are 3 customers with time frames indicated from 2 to 12, 4 to 7, and 10 to 20, and you allowed you as a shopkeeper allowed the time for the first customer to come at 2 second minute, the second customer to come at 7th minute, and the third customer to come at 20th minute. What is the time difference between 2 and 7 and 5, and 20 and 7, 13? And the minimum time difference is obviously between 7 and 2, which is 5, which is according to according to the output of this, is you get 5. But I have a better solution. If you ask the first customer to come at the 12th minute, then second customer to come at the 4th minute, and the third customer to come at the 20th minute, if you calculate the difference, the difference between 12 and 4 is 8, and the difference between 20 and 12 is also 8. So the minimum difference is obviously 8, and this will be the if you compare it with this, obviously you will see that this 8 is better. And actually, this is the best possible solution. If you have successfully designed the algorithm and output this problem instance, you will get this as the solution. So I hope the question is clear till now. Are there any questions?
So here, 2 to 12 represents he leaves at 2 and comes at 12.
No. 2 to 12 says that he is free at that time, and he can come at any point between 2 to 12 if the shopkeeper gives him that timing. But he cannot come and get the order from any point other than 2 and 12. Between 2 and 12. You get it right. You are the customer, and you have to come and get your order from the shopkeeper. But you're busy the entire day, and you're only free during this point of time, 2 to 12. So if the shopkeeper asks you to come at any point between this range, you can come and get your order. But if it's outside this range, you cannot. So the shopkeeper has to list a timing which is in this range for the customer to come. Understood?
So you can come at any point of time and take your order instantly. You don't have to spend any second. So that is the assumption. Only you come there and immediately you leave.
Okay.
The problem is clear, right? You can proceed forward. Like, you can think about the solution if you want. Maybe I'll give you 1 or 2 minutes to form some ideas about how you go about it. Like, the problem is basically simple, and the constraints from n and m is also given here. So the n is pretty small, around 8, and m is big, 10 power 5. So I'll wait for 1 or 2 minutes before you can think something. Think of some examples, some more examples maybe, so that you can get comfortable with the question. So if you are struggling, I can give you some hints. So you, as just earlier, sir has been teaching you about greedy algorithms and what is one of the prime like important parts of greedy algorithms, like one of the most important points. Like you have to order the elements of the problem in such a way that if you make a greedy choice, it is part of the optimal solution. So try to maybe think of some ordering of the elements so that you can work with by making a greedy choice. Since you know problem is going to be about greedy, just think of it in the greedy terms.
Sir, can you show the previous slide, please?
Yeah. So this is probably new flavor of greedy, which it's not a new flavor in the sense, but this is you should be having a different approach. This is somewhat it's somewhat straightforward, but it wouldn't be obvious.
So do we need to binary search for the answer?
Yeah, you have to binary search for the answer, but after that, what will you do? Like
Yes,
actually, before that, there is one step as well. Before binary search, you have to like order the elements, right? Without ordering the elements, how will you go for the binary search?
Yes,
You cannot directly apply it over there. Or you can do that after the binary search as well, during the binary search as well. It's not a problem. Actually. So yeah, as like first is the ordering of the elements. After that, if you are given that the actual, if you know that the answer is obvious L, like you can, if someone has said that the answer is L, you'll have to try and get the timings for the customers to come and get the order, such that the answer is the minimum difference between any two consecutive customers is L. So you are given L, and you are asked to get the timings. But it is also possible that for that particular L there is no possible timing. For example, in this scenario, for if you are given L is 10, obviously you won't be able to get timing because we know that the best possible solution is 8. If you are asked to find a timing for L, obviously you won't be able to. But if you are given 6 or 4 or 5, you can obviously find the timings, such that you can get the timings. So this is the second hint, and this is the third. Like as someone said, this is binary search. Like what if since you can solve these about a point, you will be able to solve for a given L. But how will you find the L? You can obviously iterate through every L from 0 to M, but there is other way of doing it which is sublinear, and that is binary search. Now we'll go for the actual problem. So we were talking about the ordering. Actual solution, and we were talking about the ordering of the customers and optimal strategy. So you can try out some common approaches. The thing about greedy is first you think of some strategy and you try your best to disprove it. You assume it is wrong and you try your best to disprove that strategy, because that will make sure that the strategy you're saying is not plainly wrong, like obviously wrong. Maybe if you're not able to disprove it, maybe it still might be wrong, but it wouldn't be such an obvious mistake. That's the way to usually approach a greedy problem. Try some common approaches, try to disprove them, come up with new approaches, try to disprove them, and if you're not able to disprove something, try to prove it. That may end up that might lead you to the solution faster. So first, let's see one. Sort by the size of the interval. Will this work? Take this example. So if we sort by the size of interval, that means the first customer has to be the one with the lowest interval margin. So one of the best possible ways to allot is at the earliest position, because if the first customer comes, we know that the customer at 7 to 10 is the first customer. So if you want the best possible timing, we have to allot the timing as early as possible, and we allot it at 7. So and for the second customer, we allot as late as possible, and that is 12. So according to our strategy, this will be the optimal solution. But I have a better solution. I have two was allotted timing for this customer as 2, so he will be the one who is coming first, not this guy. And this person will be allotted 10, and so he will be coming in the second if we order from the timings at which they come. And obviously the answer is 8, which is better. So obviously it won't be the size of the interval. What are other common approaches? Starting point. If we order the intervals by the starting point, maybe we will get optimal solution. But this is also wrong, because take these 3 customers. If we start by the starting point, this customer will be the first one to come and get their order. This one customer will be the second one to come and get the order, and this customer will be the third one to come and get the order, because 2, 4, 10. So, and still, if you want to go about allotting the timings, this will be 2, 7, 20. We'll try to allot as early as possible and as maximum as possible. In this situation, the best answer you get is 7 minus 2, and the minimum of 7 minus 2 and 13 is, which is 5. But again, I can still get a better answer, which is starting at 4. Like, this customer will be the one to come first, so he'll get his order at 4, minute 4, and this customer will be the one to come second. He'll get his order at 12, and this customer will be the one to come get his order at last, which is 20. So, but again, this is 8, which is much better. So but if the customer comes first, doesn't the customer comes first? This is the customer who comes first, because 4 is less than 12. He doesn't have the starting point, which is less than the original one. So starting with the starting point also is not a good idea. Now, ending point, you'll similarly find that there's another counter example, which is like the same as the size of the interval, I'd say. Yeah, it's the same. So, but if nothing works, what should we go for?
So starting point or ending point, can we do something like this?
Starting point or ending point?
Means both ways we can try, and then if none of them give the none of them satisfy for that L, then we can, it means we can go to another L in the search. So means what I'm saying is that either the first one will, so the last, so it can be either of 2 cases, that the one with highest RI will have the person on the rightmost side, or the lowest LI will have person on the leftmost side, like that. And then we can start.
Okay. But if it
is also not necessary that the person will at the extreme positions of its availability.
Yeah, it is not necessary that they will be in the extreme positions. That's true. Because I have given examples that they end up being in the extreme conditions, but that's not necessarily true. I'll show you a case where it is not in the extreme conditions. But
either the rightmost person, either the person with highest RI will be at its extreme position, or the person with lowest LI will be at his extreme position.
Yeah, that can be the first customer. See, the first customer who comes can have their timing at the the LA position, and the customer who comes last can have a RI position. But other than that, the intermediate, you cannot say anything about the intermediate customers. See, still now you're only I only given you examples of 3 customers because that's easy to explain or make you understand. But if you think of customers with 4, these conditions won't be satisfied. That only the customers come at the extreme points of their intervals.
No, sir, I'm saying that either the rightmost customer will be at his extreme in all the cases. I'm not talking about the intermediate people.
But who will be the rightmost customer? That's the question. Not the one with the highest RI, that's for sure, because that might be leading to problems as well. You realize that, right?
Sir,
I understand what you're saying, that the customer who comes last will have their timing at their rightmost of their RI, like that is at their RI position. But who will be the customer who comes the last? That's what I'm asking you to determine.
Sir, we can assume that that is the case, or the leftmost one is the case. So means like twice we can binary search for 2 different possible greedy approaches.
Yeah,
then,
but I'm saying your answer won't be necessarily within those 2 orders alone. Because this is I think this is not exactly a common problem, but this is at least not an obscure problem, because there is no particular order that you have to enumerate all possible orders. That is, you have to enumerate that this person will come first, this person will come second, and this person will come third. Like that, all possible approaches. So suppose if you have 3 customers, and if you want to enumerate all possible customers, you will have 3 factorial possible ordering. Like the first 1, 2, 3, 1, 3, 2, 1, 2, 3, 321, 231, 213. These are the 6 orderings.
Okay, sir, I understand. So means after I start, it won't be able to do anything. Means
Yeah.
okay.
The answer has to be within one of these things, one of these orderings, because we have enumerated all possible orderings. This is basically a sort of brute force, but you guys have missed the point that n was small enough to accommodate brute force. I told you n was less than 8, and I have even highlighted that fact. Obviously, thinking of better solutions are good enough, but it's not good enough. It's not good if you don't have proofs for it, like whether they will work or not. So since this is enumerating all possible orderings, we'll be obviously able to find one solution. Obviously, the optimal solution will be one of those orderings. We can find it. And as you said, the n was small enough to accommodate to such an algorithm. Is it clear till now?
Yes, sir.
So we have got over the ordering part. Now we'll go for the actual greedy part. So you have an order P. Here P is an array, a permutation maybe. So what it does is P is an array. The array indicates which customer will be coming first, which customer will be coming second. That is P1 will have an index. It says the first customer will be that indexed person. So you are given the input in some index, right? You will be given the LI, L1, R1, L2, R3, L3, R3, L4, R4. Like that, you will be given certain order, customers in a certain order. But this PA will be will be a permutation of that order. So suppose if P for a number 3, if P is 231, what it says is the first customer to come and get their order will be the second one which is in the input. The second customer to come and get their order will be the third one which was in the input. And the third customer to come and get their order will be the first one in the input. Understand, right? That's the order I'm talking about P, which we have just talked about enumerating all possible orders, and that is this order P. One such order P. It's a permutation action basically of 1 to n, and you are given the minimum difference between any customer L. So for that order, you are also given that the optimal solution is L. Now we have to see whether whether timings can be allotted to customers such that they follow this ordering and this minimum difference. What you have to do. So basically, you're choosing XPA. We are iterating over in the order of PA. So if it's 231, we'll first check the second customer because we know that customer is the one who's coming first. Next will be the third customer. Next will be the first customer. The one with it's in terms of the given input. So if what you're doing is Xi will be their timing to come and get their order. So XP of I will be the max of LP of I. Here L is the leftmost point, the starting point of the time frame, and this XPI plus L, PA minus 1 L plus L. This will be the XPI minus 1 will be the customer coming just before him, and he has to get after L. So basically, what does this equation mean? You are trying to see which comes first, like which comes the later one. Sorry, not first, later. So if the starting point of the next customer comes later, then the XPI minus 1 plus L. That is, after L minutes after the previous customer comes and get their order, this customer has to get their order, and that has to. And you also have to take in mind that it has to be within its time frame. So you basically are trying to restrict or put two restrictions, and you're choosing the one with the maximum. So you have two restrictions, right? Because as I said, the customer has to come basically from in the time frame LPI to RPI. So it obviously has to be greater than LPI. And the other condition is that you know that the minimum difference between any customer is L. So you have at least to place L. You have to place at least the current customer L minutes after the previous customer. So that's what this second condition means. So basically, you are taking the maximum of their starting point of the available time and the L minute after the previous customer gets. For the first customer, you can directly allot it as the LPI because he doesn't have any condition as there is no preceding customer before him. This will work. But what if this XPI plus L is greater than RPI? That's a possibility, right? If XPI plus L, that is the XPI minus 1 plus L. That is, L minutes after the previous customer comes and gets the order, for the current customer, it's out of their available time. What does it mean?
Sir, the person has to come out of its available zone. That is not possible.
Yeah. So what it means that for that particular P and L, there is no particular ordering. You can just directly say that this ordering, it's not possible. We have to move on to the next possibility. So, and basically what you're trying to, just for iterating over all possible customers, so the complexity is obviously overfed. This is it. So the basic intuition behind this is what we are trying to do is trying to fit the next customer as early as possible. Like currently you are in certain point, currently you have allotted a customer, you want to fit the next customer as early as possible. And the earliest possible time will be L minutes after the current customer, because that is the condition which we are working with. But we also have to make sure that that is within his available time frame, which is LPA. So that is the earliest possible timing for when he can come in. If you want a more formal proof, assume you have an optimal solution which doesn't match our algorithm. Obviously, there can be other solutions which is not necessarily matching our XPIs. So what we can say is, we can always say that, but one thing we can always say that is the ordering with the other one which is not following algorithm will always have their YA, if assume YA is the timing which they come, it will be always greater than XA. This can be easily prone if you start working with this equation and the order of the enumerating the order of the customers in terms of the time they come in. Like if you have permutation 2, 3, 1, if you index in the order of 2, then the second customer, then the third customer, and then the first customer, you will find that with this equation, you will find that always any optimal solution will have their YA greater than XI. So find the first I such that YPI greater than XI in terms of the order they come. Like find the first I means find the first customer in the order which they come, such that the YPI is not equal to the XPI. That is, it has to be, because we have proved that it is greater than or equal to the our solution which we have come up with. So this YPI has to be greater than XPI if it's not equal. And try to change a YPI to XPI. Since the previous until by your assumption all the previous customers have been matched with XPI, and if you change the current YPI to the actual XPI, we'll see that it won't be contradicting any of our conditions, because the XPI itself satisfies all our conditions, and the minimum requirement of L will not reduce, because we are only decreasing in the opposite direction of the next customer. Explaining this would be a bit hard, but you can try to think about it a bit more.
Excuse me, sir.
Yes.
Sir, can you please once again explain second point? Choose XPI.
So okay, what happens is basically you are given the ordering of the customers and the minimum difference between any customer. Yeah. Like any customer, I have to have at least L minutes before they come and get the order. You understood this point, right?
Yes, sir.
So now what you're doing? Yeah.
So like we will means how we will choose this L? I didn't get this, sir.
You're not choosing L. Assume you have L given to you.
Okay.
Like assume for the sake of the problem for now, you have been given L to you. It's not like you are finding L right now. You have your L and P with you, and you are trying to find the ordering for that customer, like the timings for that customer, for that orderings and L.
Okay. So, yes, sir.
So what you are doing is basically until assume you have allotted all customers before until PI minus 1. That is, if it is 2, 3, 1, you're currently working with the third customer, you assume that the second customer has been already allotted the timing. So what you're basically doing is you want the current customer to be at least L minutes away from the previous customer. That is what this condition is for. You understand this? Like this means that from the previous customer, you are L minutes away. But it won't do if this L minutes away is before even his available time frame starts, because that would be, then you won't be able to communicate it. But it's not a problem if he comes at the LPA, and if this LPA is greater than this, because it will anyway be at least the difference of L. We don't have to be the difference to be exactly L.
Sir?
Yeah.
Sir, what is LPI here?
Yeah, LPI is the starting point of the L is the starting range of the time frame, right? L and R are the starting point of the time frame. Like starting by L is the starting point and R is the ending point of the time frame. PA is the customer, like the order of the ith customer in terms of timing. As I told you, this permutation denotes the order of the timing the customers come in. So LPA is the starting point of the time frame of the ith customer which comes.
Okay.
And
Okay,
XPI
sir.
minus 1 will, yeah.
Sir, how can we choose L before? Since L is a big range, varying from 0
Okay.
to M.
Yeah, that's why I'll come to. For now, assume you have been given L.
Okay.
So what you're doing is you're choosing XPA, and if XPA is out of the range that is greater than any possible is time frame, you obviously for this particular ring it is not possible. So what, as I said, the intuitive way to reason this out is you are trying to actually fit your customers as early as possible. And for the formal proof, this is in mathematical terms, but if you want to say it in simpler terms, if there is any other solution which is not matching our optimal approach, like obviously the time difference will be the same, just the timings will be different. So what you're going to do is the first thing is we have to prove you have to prove is all the timings which you get in the later the solution which is not matching our greedy approach. So we have a greedy approach and we have some certain XPIs, right? We are got it with using this algorithm. But if there is some other solution which is a set of YI which do not match our XPIs actually. So what you do is first try to prove that all those YIs will be greater than Xi, which can be proved with inductions. See, these inductions and others, I think in discrete structures you have discrete structures right now, right? You will be proving all these methods of proofs. And induction is one of the more common ways people will go about it, and contradiction is the other one. So in induction, you can prove that using induction, you can prove that YI is always greater than Xi for all possible for all the customers. And the next you go about is if there is a I which is not equal to our XPI, that will obviously be greater, because if it's not equal, because it's greater than equal, it will be greater than. And what you try to do is change the other solution to match our XPA and prove that our solution still works. That is, all the solution which doesn't match our greedy solution can be actually converted to a greedy solution. That's what I'm trying to prove in the formal proof. It won't be that simple to explain, because since this is an online system and I don't have any digital board to work with, I couldn't really do much to explain this, but try to wrap your head around this.
So, sir, isn't it a brute force method? We are checking all possible orders.
Yeah, we are checking all possible orders P, and for that for now I am not saying how we are checking, how we are getting L, but I'm just saying you are given L. Like I will be explaining. Now we'll go to. I'll give you an example of how this greedy strategy works. Suppose you have 4 customers, and their available time frames are 8 to 10, 4 to 7, 2 to 10, 5 to 14 respectively. You want to check whether a minimum difference of L is equal to 4. That means between any 2 customers, at least 4 minutes gap is there, and for the order P is equal to 3, 2, 1, 4. That is the customer with the range 2 to 10 comes first. The customer with 4 to 7 comes to second. 8 to 10 comes first. No, sorry, my bad. The customer 2 to 10 comes the first, because that is the third in the input. The customer with 4 to 7 comes second, and the customer with 8 to 10, which is 8 to 10 comes the third one in terms of timing, and 5 to 14 comes the last. Now we want to check whether this will try to solve this instance using our greedy approach for the first customer. Since it's the first customer, we directly give you the assign the LI one, because that's the as earliest point as you can. And since we start the first customer is 2 to 10, we are allotting to the 2 to 10 customer. Now what is L? 4. So what we are basically doing is in this equation, remember this equation, because I won't be coming to this again and again. So LPI, max of LPI, XPI minus 1 plus L. Now, the previous xpi minus 1 in this case is 2. And L is 4, so 6. And what is the LPI for this one? 4. So the maximum of 4 and 6 is obviously 6. This red dot corresponds to the 6th minute. Now, we know the next customer which comes is the one with the first in the input, which is 8 to 10. And what is previous one was 6. 6 plus 4, that is after 6 plus 4, L is equal to 4. 10. That is in the 10th minute he can come and get it. And what is his LPI? LPI is 8. So 8 to 10, obviously maximum will be 10, and he can come and 10. And 10 is not obviously out of sight. It is just at the border, but he somehow managed it in the border itself. Now what is the next one? 14. Similarly, using in the equation, you will be generating 14 plus this for the 4th customer. And since all customers have been allotted with the given conditions, for this order, for this particular order and particular L, particular order P and particular order L, it's working. Now take this example. Similarly, same input, but different order. Yeah, different order. Which is 3. Here it was 3214. Here it is 3124. So that is the first customer will again be 2 to 10, but the second customer this time will be 8 to 10, and the third customer will be 4 to 7, and the last customer will be 5 to 14 again. So since we saw.
So means within each permutation we'll greedily put the orders.
Yeah.
Okay.
Within each person we will do. Okay, there's a mistake in the order. It's not 3124. It should be 2314. Yeah, it's 2314. This is my bad. It should be 2314. So the first customer is the first one to come will be 4 to 7. He will be allotted 4. That is the 4th minute. He will come at the 4th minute, because that's the earliest possible for the first customer. And the second customer will be L is again 4. So 4 plus 4 will again be 8. And the starting frame for this customer is 2. So it's well within the range. So we'll just be giving 8 to this customer. And for the next customer though, if you want to allow, because the next customer, which is, since the permutation will be 2, 3, 1, 4. This is a mistake. When I'm sharing it with you, I'll change it and share it. But the third customer, when the third customer in terms of timing is 8 to 10, and if we have plus 4 from the previous timing was 8. 8 plus 4 will go 12, and but 12 is outside this time frame. It's exceeded its time frame. It's not even before the time frame. It exceeded its time frame. So you cannot allot a timing to this customer for this order, which ensures that the minimum difference between any two customers is 4. That is L. You understand, right? Is this clear till now? Like there are 2 examples. There was a typo in this one, but other than that, this should help you understand how the greedy strategy is being applied for each permutation. And till now this works. Now, how do you efficiently find L? Someone said binary search in the initial. I'm not sure how many of you worked with binary search, like for finding other than arrays. So until now, most of you only have used binary search in arrays. Is that the case? Like, or is everyone familiar with using binary function using a normal predicate or something? Tell me, have you guys used it? All of you used it in situations other than using in arrays, binary search.
Only in arrays, sir.
So till now, you only worked with arrays. So that's why I try to make it converted into a fashion that you'll understand. So obviously, efficiently finding it. So we have till now seen the case of if you are given P and L. For P, we have seen that we'll be enumerating all possible P's. But how are we going to do L? Are we again going to try out all possible L's? That also works. But obviously, M is 10 power 7. So you'll be enumerating L from 0 to 10 power 5. But that will obviously take a lot more time. I am saying there's a better solution. If you notice one important observation, if for a particular L is equal to X, if it is not feasible to get the greedy strategy, that is, we encountered with such a situation where we are not able to allow the timings. For that case, if it is not possible for even L is equal to X, for any L greater than X also it will not be possible. because if that was possible, we can obviously work with this also. So you realize that it follows a monotonous property. So what I am doing is try to create an array A, like where A is possible of I. That is, the array length of the array will be from 0 to length of the array A will be m, where the ith index represents whether is possible of I. That is, if is possible of I, that represents that it returns 1 if there exists a timing. That is, you can assign the timings to customers such that for that particular P and I, you can assign the timings, or 0 if it is not possible. Then from the previous property which we have noticed that the array will be some values of 1 and then some values of 0. Obviously, it will be strictly decreasing 1, 1, 1, 1, and 0. So this is an array with strictly decreasing property. And obviously, this means that we can use binary search. Now, what you have to do in this binary search? You have to find the index of the last one or the first 0, according up to you. So if you realize that if you find the index of the last one, that means that is the maximum possible L for which you can assign timings for that particular order. Got it? So in binary search, like this is a pretty common approach in array, finding what is the last in a sorted array, finding the last occurrence of a particular element. This is a very common approach. You can look it up or even work it out yourself. If you know a normal binary search, this shouldn't be that hard. The advantage of this approach is that you can solve it in O of log m. O star in the sense that we are only looking in terms of only this m parameter. We are not including n yet. So for this binary search, we'll be able to finish this in log m.
Excuse me.
Yeah.
So in second point, what is x?
X is some random value, some random x. Assume that if it is not visible for some random x, which is in this range, 0 to m. If it is not feasible for one such x, we can obviously conclude that it will not be working for any other such L greater than x, right? Because even for a smaller value, it is not working, means for a larger value, it won't work. Think of it like that.
Sir?
Yeah.
Sir, if we sum this array of AI, so we will get the like I know, sir. A1 is equal to is possible of 1, and
yeah.
So means for a particular L greater than 8 would be 0. So the maximum element would be suppose I. So if we sum the whole array, so it would give I minus I, sir. 0 to I.
Okay, but the point, so yeah, that will give you I. But the point is for you to calculate the entire array, at least you have to go, the worst possible case will be O of m, right?
Yes,
so,
sir.
See, that is in the assumption that you know the entire array, but we are not actually working with the entire array. So you don't create the array before you start binary search. You create the elements as you binary search. See, in a binary search, you only access only O of log m instances. We do not access the entire array, assuming that the array is sorted. The only fact you need to know is that the array is sorted, and what you will be doing is you will be performing binary search on the array and generating the element on instance basis. So suppose you are binary search and you only assume that m is 20, but when you're binary searching, you will be accessing only 10, instance 10, instance 5, instance 2, instance 1, similarly, not more than 5 instances. You get it? So what you will be only doing is generate. See, every time you're using is possible of I, right? What you will be doing is you are performing this greedy strategy, which we have talked about, this one. So further it takes O of n. So every time you calculate an index of I directly, you will take O of n. So that's why we're trying to make it such that we want the A of I to be as small as the number of values you're calculating for the instance is very less as possible. But
Sir,
you know the fact that A is decreasing. Yes.
Sir, for a given order of P, we have to find all the possible values of L that are feasible, right?
Why do we have to find all possible? We only caring about the maximum L, right? Which works.
Sir, yes, sir. Sir, how we can do that?
Yeah, that's what I'm saying you, right? You understand this array will be series of ones and zeros?
Yes, sir.
So now what you have to do is you have to find the index of the last one. That is which index has the last one in the array. If you find that, that will be the maximum possible L.
Yes, sir.
So that is the maximum possible L for which you can allot a timing. Because after that, all other timings are not possible.
Yes, sir.
So this is a very common approach in binary search. If you haven't solved such a problem,
Sir?
you have to solve it because this is very quite a common problem, and this is one of the basic problems in binary search as well.
Sir?
Yeah, Thomas. Yeah.
Sir, if the values are not integers, then how will we stop the binary search?
Yeah. So that's a complicated, a bit more complicated binary search. But in that case, in the question they will be mentioned that what is the precision you want in the minute. I mean, if it's not a, I mean, if it's not an integer, it can take any decimal point. It cannot be completely precise because if it's not a complete rational number, if it's suppose 8 by 3. With 8 by 3, it will keep on going. We will not be able to output the entire complete one, right? 1.666. We have to round off at some point. At some point, we will be making the continuous number of 6 or 7. One point we will be making the 7. So what you will be doing is we are looking for that precision. They will mention it in the question what is the precision they are looking for, and once you're looking for L, in that case this imagination of array A won't work. In that case, you have to go look up binary search. Go look up for binary search with predicate. I suggest aggressive cows. It's a very common problem in sports. I suggest all of you to solve it to get a hang of how to go about this normal binary search. And it is such a famous problem for this topic that there's a tutorial for there's almost hundreds of tutorials for that problem. You can see you'll obviously find one that explains it in a very easy way. The problem is aggressive cows. You can note it down if you want. So this is the problem. This is quite a famous problem. There are so many YouTube videos, so many discussions, so many Medium articles. You will obviously find one article which explains how to do a normal predicate binary function properly. So in a case where decimal, if you are looking for a decimal value L, what you will be doing is looking for the change in precision. If suppose your current mid is in binary search, you will be using a mid term, and if your current mid is 10.50001 and your next mid is 10.50015, and the required precision is only 10 power minus 3. That is, you want your answer to be within 10 power minus 3 of what the actual answer is. Obviously, this is within the precision. We can just stop the binary search there. As long as you reach the precision you want, you can stop your binary search. That's why I didn't give you the decimal one, because it will be a bit complicated for ones who have just started learning binary search. You can look up some similar problems for this, but I suggest you start with aggressive cows. So again, obviously the complexity will be O star log n. So we are since we are almost running out of time, I'll try to wind up fast. So efficiently finding L. We have now found L. Now, how do you enumerate all orders? I have just glimpsed over it, but it's not that obvious. One obvious way would be to use next permutation. Next permutation is a function in SQL, which if you give it an array, it will give you the next permutation of the next lexicographicaly smallest permutation after that array, and it will return whether it has reached the maximum permutation. Suppose if you are given 1, 2, 3, the next if you pass it to the next permutation, it will give you 1, 3, 2. That is the next lexicographically smallest. And if you have passed 3 to 1, it will return false because there's no lexicographically smallest permutation after this. So that's how next permutation works. But obviously, sometimes your assignments will be banning you from using SQL. In that case, what are you going to do? You can go for a simple recursive strategy. Since we are short on time, I won't be explaining a lot on this. But have a look at this algorithm. So if you will be passing 2 parameters, and I mean, just look at this. If you want, you can just pass some array of size 2 or 3 to this function and see, or implement in C++ and see how it works, and I think you'll be satisfied. I'll share you the slides if you want. And this is recursion. So I don't think you guys know it yet, but every time you call a recursion function occurs, right, you will be increasing your internal stack size. So in short, all recursive functions are slower than your counterpart iterative functions. Like, you can just have it as a fact. You will be studying it in OSS or some, like, later when you go for other core subjects. But the thing is, most of the pretty much most of the time, all recursion functions are slower than their iterative counterparts because of this stack size. But it's not significant in our case. But it's still a problem of efficiency. So what we are going is for an iterative function. I'll just give you a rundown of what is happening here. In the first 4 lines, I'm trying to find the last position I, which such that AA is less than AA plus its successor. That is, AA is less than its successor. If there's no such I which is encountered, you realize that it is just an array with completely descending order. It's an array completely ordered in descending order. Understand, right? Because if you find no element which is greater than your previous element, obviously it is a descending order element. So it is completely ordered in non-increasing order. So I'll written false because there's no better lexicographically smaller array. But if it was there, I'll swap it with the next. This is the condition to find the index which is just greater than the one found I, which is greater than just a pos. That is the pos which you found here, which is just greater. So I increase the swap pos. It's actually swap pos minus equal to 1, but whatever. And I swapped it and reversed it. This is again, these are pretty common algorithms, and I'm not able to explain it because of the time constraints, but you can look this up, or if you have any doubts, you can post it in the queries channel. So basically, I'll try to summarize the solution. So, the solution is in pieces right now. I'll try to piece them together. And if you'll, yeah.
Sir, what was the problem with the recursive one? I didn't.
So it's not a problem. It's so basically what you're doing is you're saving all the permutation to this every time. So suppose you have 8 factorial permutations. So what you're doing is actually consuming 8 factorial into n space. Here, right? Because I'm asking you to, in this recursive one, I'm asking you to save permutation A every time this works.
Yes,
and this will occur at least n factorial time. So you are actually saving n factorial permutation simultaneously. That's obviously memory costly. And the other fact is how a basic recursion algorithm works. Every time you call a recursion algorithm, there is an internal stack which gets increased. Your stack size keeps on increasing. And since this is quite a lot, n factorial stack, and each stack space is not small because it's obviously at least n. So these are these are details which you will be learning later in OS, how OS or compilers, how things will be, how things will happen when a recursion occurs, what happens to the stack and all. But in short, these are memory costly approaches and take a lot more time in general, especially recursion. So that's why I'm trying. This is a iterative approach with user. Basically, the next permutation function in the SQL also uses this iterative approach. Yeah.
So next permutation is also the same algorithm, or is it better than this one?
It's probably the same as permutation iterative. Because you cannot do better than O of n, obviously. That's for sure. You cannot do better than O of n, and most probably they have a bit more efficient approach in the way they implement, but the basic algorithm will be this only.
Okay, sir.
So now I'll summarize the solution. So we are seeing ways to enumerate all possible permutations. So you try to enumerate it like that. And another point to note is that in this, I am returning true or false. if I'm returning true in the sense that there is a next possible lexicographically smallest available. That and actually the next permutation will be actually modified in the pass array. This is actually pass treat it as something passed by reference. I'm actually changing the output in the actual given input itself. So I'm giving you the all possible. You have to enumerate all possible permutations, and for each permutation, binary search. We are talking about binary search, and binary search is the minimum time difference between any consecutive customers. So that's what this is about L. We are trying to binary search L, and for each and how will you say whether if a particular combination works? That's why the greedy strategy we talked about. See, determine whether if the greedy strategy is possible or not. If it is possible, go for the upper half of the binary search. If it is not possible, go for the lower half of the binary search. Then take the max. So now for each of the permutation you did this right. Now take the maximum L you got across all possible permutations. We have to do that because we have seen that no particular order in particular works. And talking about the complexity, enumerating all permutation takes n into n factorial, and binary searching for the optimal minimum difference will be O of log m, and checking feasibility will be for each feasibility takes O of n. So the basic complexity will be O of n square n factorial log m. And since n is quite small, this will run in all missions. N is less than 8 only, right? So it can work in all missions pretty fast within 1 or 2 seconds. These are some other problems which I have given you. I have taken it from Mohammed. Yeah.
Sir, why is it n squared times n factorial log m? Why isn't it n times n factorial log m?
Because there is a n when you're applying the greedy strategy as well, right? So permutation itself takes n into n factorial.
But that is just a plus, right? So it's n times
it won't be a plus. Okay. Okay, my bad. It should be n factorial into n only. My bad. I'll make all the corrections and I'll make all the corrections and share it later.
So can't we simply write n factorial? I mean, does it matter? N into n factorial?
Not necessarily. No. I mean, it's pretty much the same.
Yes.
But to make things clear, I'm just writing this down. But if it is some other higher order terms like n square, even n square, I don't think even n square matters. Yeah. As long as this power is finite, I don't think it matters.
Yes, sir. Because it is always less than n plus 1 factorial or n plus 2 factorial.
Yeah. Shouldn't matter. But to make things clear, I just listed it out here. So here I have basically listed out some other problems. I think you guys want to go for lunch or something. You're probably time's up. So I've taken it from HackerRank only, and I've given you some short hints how you can go about it. You can maybe ask it in the Teams channel if you have any doubts about this. And yeah, that's all. Like I have given you a bonus as well. So the solutions are also there. So you shouldn't be having a problem, to be honest. But yeah, if you still have a problem, you can ask me. That's all. If you have any problems till now, you can ask in the previous problem or something, or in the way you iterate the next permutation. Nothing. If you're done, you can leave. I will share the presentation by today evening.
Sir?
Yeah.
Sir, I have a general doubt regarding this O of n factorial, sir. O of n plus 1 factorial, I mean n plus 1 factorial and n factorial are not of the same order, right?
Or not of the same order, but in terms of remember that our complexity is asymptotic notation. That is, we are treating only for n in terms of infinity. So if it's in terms of infinity, if it is n factorial, n plus 1 factorial are nearly the same.
Sir, but that limit notation, that will not be something finite. So we can't say that they are related by a theta notation, right? N plus 1 factorial and n factorial.
See, for our comparisons, this works. N factorial works. if you are comparing it with some other, if you want to say, if you are asking me which is better, n factorial is better than n plus 1 factorial, in terms of asymptotic notations, they both are actually equal only.
But sir, we cannot write n into n factorial as big O of n factorial.
Can't we?
Yes, and no valid C will work because we can always find an integer greater than that valid C which will violate the condition.
N factorial. Okay, I'll maybe look this up and I'll inform you. But yeah, probably shouldn't be. Okay, I think they both are not same. But I'll confirm this once again and tell you. Okay. Any other doubts? So another one thing is, I remember some of you asking problems to solve. Instead of just randomly solving problems, you can look at the particular topic you want to solve in HackerRank, or there is another place which you might want to check out. CSES. I wouldn't say that it has topics on all problems on all topics, but it has quite a lot of topics. So there are over 400 problems here. So some of them are advanced topics, but there are basics as well, like tree algorithms, graph algorithms, then DP, sorting, searching, strings. You can check them out. It's quite a good site. Yeah. Anything else? Okay then. Bye. I'll be leaving.
Thank you, sir.
Thank you, sir.
Yeah. Welcome.
Sir, stop the recording.